So thus far we've talked about a couple of applications of energy, of energetics ideas. One application that we've talked about so far is this sort of idea that you can use energy for the purposes of validation. So it's a good way to actually check that things are actually working in your system, and can often be helpful for thinking about where things start and where things go to, and that's some of the things that you've worked on in the first part of this module. A second idea that we've talked about a little bit with respect to the utility of energy is the idea of using energy as one of the conserved quantities, so sort of combining this sort of idea of conservation with before and after thinking in order to figure out what the final state of a system is given the initial state of the system. And that, again, is something that you've spent some time sort of thinking about and playing with in some of the module problems. There's a third really big idea, and this starts to move us in the direction of Lagrangian mechanics, but it doesn't quite get us there yet, which is the idea that sometimes it's actually easier to think about system behavior with regard to how energy depends on the system's configuration, as opposed to thinking about how forces depend on the system's configuration. So our sort of usual approach for things is to actually start with forces and then use forces to figure out equations of motion, and use forces to figure out what the energies are, right? So we've used force to figure out what the potential energy is. You use the equations of motion to figure out what the velocity is in order to figure out what the kinetic energy is, and so forth. But you also have the option to instead of starting with forces, you can also often start with energy, and then from energy figure out forces and equations of motion. And what I'm going to talk about in this video and the next couple of videos is this sort of idea of going from energy to forces. Okay, so how do you, if you know what the energetics of a system are, how do you use that information to figure out what the interactions are, what the forces are? So let me, first I'm going to do some very simple examples of that in one dimension, and then we're going to move into multiple dimensions and introduce a little bit of mathematical ideas that we'll need to deal with this more generally. And then finally we'll tie these ideas back to some observations about kind of the way the world works in general. So let's start with the sort of 1D examples of this idea that you can start with energy and go to forces. And in order to introduce those 1D examples, let me first remind you that we've actually gone from forces to energy, particularly to potential energy in the past, right? When we figure out what the potential energy is, what we're doing is we're asking the question, how much work do we need to do against some conservative force in order to move the system from one configuration to another configuration? And so the way that we write that mathematically is that we integrate from some starting position, which we say is the sort of starting configuration or the zero energy configuration of the system, to some final position, which I'll call R. So this is the potential at some point R. And we ask the question, how much force does the interaction that we're interested in exert at a given location? And we're sort of walking along some path to get from the origin point to the point R, and asking the question with this negative sign, how much work do we have to do? That is, we're pushing against the force that the interaction is causing. So for example, if we're talking about gravity at the Earth's surface, right, we say, okay, the Earth's surface is my origin point. I'm interested in carrying some object up to some height h, and so I'd say the potential energy as a function of the height above the Earth's surface is minus the integral from y equals 0 to y equals h of minus mg in the j hat direction dot dy j hat, right? So dy j hat is this dx, mg j hat with a negative sign is the force. I pick up the additional negative sign, and not surprisingly, I get mgh, right, is the potential energy. You've seen that before. It's not a terribly surprising result. By the same token, I can do the same thing with a spring, right? So I think about a spring, right? When it's at rest, I'll say that the rest position is the zero energy position, and I'm going to stretch the spring from here to here. And when I stretch that spring to some position x, right? So the potential at some position x is the integral of negative the integral from the origin point to that length to that position x of the force that the spring applies, or the force that the spring applies is minus k times x I hat dot dx I hat, and not surprisingly that gives me another result that you've seen before and know, which is the potential energy is 1/2 kx squared. So these are examples of going from the force to the energy, but I want to sort of highlight something that you'll remember from calculus, right? I'm figuring out what the potential energy is by doing the integral. I could conversely ask the question, if I know the potential energy, what's the force, right? So to go from potential energy to force, I just have to take the derivative of what that potential energy is. And of course, because there's a negative sign here, I'm also going to have a negative sign here, right? So if I go to look at this sort of first example, for example, the gravitational force is minus dv by dh, right? Or minus mg. And you should be having a few questions about what's going on from a vector perspective here. This is a vector on the left-hand side, looks kind of like a scalar on the right-hand side, and I somehow have to take into account what the sort of directions are here. In this case, my path was in the j-hat direction, so I'm going to right now just sort of magically put in a j-hat. And by the same token here, if I ask about the spring force, it's going to be the minus the derivative of the potential with respect to position in the I-hat direction, or minus k times x, right? Because the derivative of 1/2 kx squared is k times x in the I-hat direction. So these are some examples of how, if you know what the potential energy is, you can actually figure out what the force is. But there's something that we need to introduce, and we'll introduce it in the next video, that allows us to actually think about this potential as being a vector valued, or think about this force as being a vector valued function that's derived from this scalar function, which is the potential.